The sun, an immense fiery orb in the sky, has been a source of wonder, mythology, and scientific inquiry for as long as humanity has gazed upward. At first glance, it might appear as nothing more than a bright, unchanging ball of light. Yet beneath its blazing exterior lies a world of activity so intense and complex that it has taken decades of technological innovation to begin to understand it. Today, let us embark on a journey into the sun, not just to its surface but deeper, exploring the remarkable layers and phenomena that define our closest star. Using modern tools like advanced telescopes and spacecraft, we have reached farther than ever before into the heart of the sun's secrets. What we have uncovered is nothing short of extraordinary. Peeling back the layers of the sun. Much like peeling an onion, the sun reveals itself layer by layer. Let's start from the outside and work inward, encountering some of the most fascinating features of our solar neighbor. The corona, a crown of mystery. The sun's outermost layer, the corona, extends millions of kilometers into space. Despite being far from the sun's core, the corona's temperature soars to several million degrees Kelvin. This counterintuitive fact that the corona is hotter than the surface has baffled scientists for decades. What could cause such extreme heating? One leading theory is that magnetic waves generated by the sun's turbulent plasma accelerate particles in the corona, depositing immense energy there. Another involves small, frequent eruptions known as nanoflares that release bursts of heat and energy. Regardless of the cause, the corona's dynamic behavior is visible in the spectacular displays of solar flares and coronal mass ejections, CMEs. During a total solar eclipse, the corona becomes visible as a glowing halo around the sun. Advanced instruments, such as those aboard the Solar Dynamics Observatory, SDO, let us observe the corona at extreme ultraviolet wavelengths, unveiling details invisible to the human eye. The chromosphere, dancing jets of plasma. Beneath the corona lies the chromosphere, a region that appears reddish during solar eclipses due to the emission of hydrogen alpha light. This layer is home to spicules, jet-like bursts of plasma that shoot up to 10,000 kilometers into the corona at speeds of 100 kilometers per second. For decades, the origins of spicules were unclear. However, modern computer models incorporating neutral particles alongside ionized plasma revealed that these neutral particles provide the buoyancy needed to launch spicules skyward. The chromosphere also experiences coronal rain, a phenomenon where cooled plasma condenses and falls back to the sun's surface in shimmering arcs. The photosphere, the visible surface. The photosphere is the sun's visible surface and the layer we perceive when looking at the sun, with proper eye protection, of course. Although it appears smooth and uniform, closer inspection reveals a granular texture resembling boiling water. These granules are convection cells roughly 1,000 kilometers wide, with hotter plasma rising in the center and cooler plasma sinking along the edges. Sunspots, darker regions on the photosphere, are areas of intense magnetic activity where the temperature is slightly lower than the surrounding surface. These spots often serve as the birthplaces of solar flares and CMEs. Deeper than the surface, the sun's interior. Now, let's dive beneath the photosphere, venturing into regions of the sun that are not directly observable but can be studied through indirect means like helioseismology and computer simulations. The convective zone. Churning seas of plasma. Beneath the photosphere lies the convective zone, where hot plasma rises toward the surface, cools and sinks back down in a continuous cycle. This churning motion generates the sun's magnetic field through a process called the dynamo effect. The radiative zone, a slow journey for light. Further down, the radiative zone is a region where energy moves outward primarily through radiation. Photons generated in the sun's core take thousands, or even hundreds of thousands of years to traverse this dense layer due to constant absorption and re-emission. The core, the furnace of the sun. At the heart of the sun lies its core, where temperatures exceed 15 million degrees. Kelvin and pressures are unimaginably high. Here, nuclear fusion occurs, converting hydrogen into helium and releasing the energy that powers the sun. This process generates vast quantities of light and heat, which eventually make their way to Earth, sustaining life as we know it. Tools of exploration. Over the decades, humanity has crafted a set of cutting-edge tools to unravel the sun's mysteries. These technological marvels, in the form of space missions and observatories, have revolutionized solar science. SOHO, Solar and Heliospheric Observatory. Launched in 1995 as a joint project between NASA and ESA, SOHO has provided invaluable data about the sun's atmosphere and interior for nearly 3 decades. Its suite of instruments allows us to study solar oscillations, track coronal mass ejections, and monitor the solar wind that flows outward from the sun to the edges of our solar system. Parker Solar Probe. An unparalleled mission, the Parker Solar Probe is humanity's closest approach to the sun. Launched in 2018, it aims to touch the sun by traveling directly through its corona. The spacecraft's advanced heat shield protects it from temperatures reaching 1,400 degrees Celsius. By studying the corona up close, it seeks answers to long-standing mysteries, such as why the corona is hotter than the sun's surface and how the solar wind is accelerated to high speeds. Solar Orbiter. This mission, launched in 2020, is designed to provide the most detailed views of the sun's poles, regions crucial for understanding the solar dynamo and magnetic field generation. Equipped with advanced telescopes and instruments, the Solar Orbiter captures high-resolution images of solar activity and measures its influence on the heliosphere. Why does it matter? Studying the sun is not just an academic exercise. The sun's activity has profound effects on Earth, influencing everything from climate to technology. Solar storms, for example, can disrupt satellites, power grids, and communication systems. Understanding these phenomena helps us predict and mitigate their impacts. Moreover, the sun serves as a natural laboratory for studying fundamental physical processes. Insights gained here can be applied to stars throughout the universe, expanding our knowledge of astrophysics and the cosmos. Looking ahead. The sun remains an enigma in many ways, yet each new discovery nudges us closer to understanding its mysteries. With every technological leap, we peel back another layer of its secrets. Who knows how much deeper we might delve into our nearest star in the years to come? Perhaps future generations will unlock the mysteries of the sun's core, uncover new dimensions of its energy, or even devise ways to harness its immense power for humanity's benefit. The possibilities are as vast as the cosmos itself. For now, let us take a moment to appreciate the sun in all its magnificence. It is not just the provider of light and warmth, but a beacon of inspiration, guiding our pursuit of knowledge and exploration. As we continue to study this celestial giant, we're reminded of the intricate connections between the sun, Earth, and the universe. If you found this journey into the depths of the sun fascinating, don't forget to like this video, subscribe to our channel, and hit the notification bell so you won't miss out on our next exploration. Let's continue unraveling the wonders of the universe together.